Hi, my name is Leland Curtis. I'm co-leader of Computational Design within SmithGroup's Technology and Practice Group. Today, I'll be giving you guys a repeat of a presentation that Dr. Richard Mistrick and I gave at this year's Advancing Computational Building Design conference. So last year, Dr. Mistrick joined us on sabbatical to look into a variety of different computational design methods, and what we were exploring in particular is this topic called design space exploration, which is what we will be going over today. So design space exploration. In short, this is a digitally native design process that leverages parametric modeling and computation to approach problems differently. And it's pretty exciting, and we want more people to know about it, so that's what we'll be going through. And it solves a fundamental problem, something I would call a problem, with our current design process. So we seem to all be stuck in a validation process because of a simple truth, that in order to analyze a design, we need a design to analyze. So shown here, this is what I would call the validation process. We design something, we then might send it off to engineers or consultants, we'll analyze it, understand it, right, run it through our programs, draw some information out of that analysis process, feed it back into our design process, come up with something new, tweak it, change it, and then we analyze it again. And now notice in all of this that the analysis has to occur after the design decisions have been made. Because again, we need a design to analyze. And the benefits of that are limited. Very often, the information we get out of this process tells us how we did, but it doesn't often tell us how we can do better. As soon as you ask that question, okay, here's how we're doing, well, how can I do better? We almost immediately start relying on best practice, rules of thumb, experience. And we have to then interpret, almost like reading tea leaves, interpret this analysis that's based on an old design in order to understand how a new design might perform. And this is limiting. And if we could do anything, if magic were real, we would love to know all of this before or while we're making our design decisions, right? I want to understand the impact of my design decision as I'm making it, or before I've even decided to make it. And in a way, this is what a good engineer or a good consultant would do. If you have a lot of experience, if a designer says, well, what if I try this? You might, standing in the room, say, I've done that before, it's probably not going to work well. Or these are the design decisions you should focus on most because based on my experience, I know they're going to be most impactful. We want our analysis tools to work this way. And I'm excited to say that this is now possible. Computation, parametric modeling enables a new way of designing that can break this validation cycle and provide real-time analysis, provide ways of informing design decisions while we're making them, which is why the title of this presentation said we're informing at the speed of design. So this is all possible through design space exploration. And it's possible because the world has changed, right? We now have parametric modeling with Grasshopper or Dynamo. We have massive computing resources, whether that's cloud computing or just your laptop, right? Your iPhone has more computing power than what they sent to the moon. People always say that. And this is improving every day. So what was not feasible yesterday is now feasible today. And also we have a variety of very advanced algorithms through machine learning or just better statistical methods that enable us to learn from data in ways that weren't possible before. So parametric modeling, massive computation, and the ability to understand and leverage data, all of this has changed, and all of this should change our design process. So design exploration has three basic steps that we're going to be walking through today that make all this possible. And it, simply put, begins by modeling your challenge parametrically, then generating the design space, and then exploring the design space. So let's break down each of these so you understand what I'm talking about. Now, the first one, model the challenge. This is the linchpin. This is really the most important part of the whole process. And this is the idea that a model should not be seen like this. Our design should not be seen as static single items because the design process is always fluid, it's always changing. When I say model, I don't mean this. When I say model, I mean more like this. I mean more of a map, a web of logic, a system. Now think of climate models, economic models, right? Parametric models are more like an economic or a system model than a physical 3D model. And that's hard, I think, for designers to break out of because we're so used to working on a single design. But a parametric model, broadly speaking, is a connection of the logics that say, given these design decisions, this is now my output. So if you can model not a design that you're going for, but instead try to model the challenge you're trying to understand, it opens up a lot of possibilities. So here's an example of that. So right, what am I talking about? Here is an example of a model of a shading system challenge. So rather than modeling a particular exterior shading device as a singular design, instead we modeled all possible shading devices, where, as we go through here, this little tool allows you to adjust, say, the orientation, that's one parameter. Maybe it's the depth of the shades. Is it an overhang? Is it vertical louvers, horizontal louvers? What's the rotation, the spacing? These are all different design decisions we can make. And the point here is not to understand how any single device works. It's to understand how shading devices work in general. Because as I play with these different parameters, I can start to understand and learn and explore the problem. And once I understand the problem, I'm now informed. Now, as I'm making design decisions, I can understand them in real time. This builds up my experience. And also, again, we said we don't want to wait for a design and then test that preconceived design. Here, I'm able in real time to explore how shading devices work to then arrive at a solution that's most appropriate for my unique design condition. So again, modeling the challenge. The goal is to understand, not to quickly arrive at a preconceived idea. So once you have a parametric model that can be any design within your challenge, you can then generate the design space, because in a way that parametric model represents all possibilities, and a design space is the landscape or the space of possibilities contained within that parametric model. And when we generate the design space, what I'm referring to is simulating a variety of places within that parametric model, essentially creating a giant database of design data, where every row is a different option, and every column is a different feature. Now, this is super confusing, almost intentionally done so. So let's look at it visually. We're all visual thinkers. So let's consider a basic facade with 3 parameters. I'm going to explain what a design space is. So this is a parametric model and how we often think of parametric models. So as I change one of these parameters, you can see that the facade is changing. So what I want to show here is that this parametric model can be any of these design options, right? As you see this moving, it can be any of them. But we're still looking at it as if it's a item. Yeah, it's moving, but it's still a single design at a time, one design at a time. And that's not the right way of looking at a parametric model. The analogy I heard was, imagine a movie. When I say I love Gladiator, it's one of my favorite movies, I'm not referring to a single still shot, picture frame of that movie. I'm referring to the totality of the movie. Well, likewise with parametric models, if all we're looking at is a single frozen frame, let's say this design or this design, we're not understanding the larger whole, and we should really consider parametric models as all of the possible designs contained within them. And that would be a design space. So let's look at a design space this way. Let's break down that parametric model and unroll it so that we can see the entire thing at once, which is a different way of looking at it, right? Let's break away from optioneering. We're no longer looking at 1 or 2 options. We're looking at the whole space of possibilities. So we had 3 parameters. Let's roll them out. So if we change the window width, we know that we can have all of these different designs. Now let's add another axis, fin depth. As we adjust those, you see we start to get an array of possibilities. Now we add a 3rd dimension in here, ceiling height, and you'll see that we're now creating a space of design options. But again, let's stop looking at them as design options. Let's consider each design a point in this space. A point defined by its position, its coordinates in that space. And now this is going to go a little bit strange. Let me see if I can pause this. 3 dimensions we can visualize and we can understand. But most of our designs have far more than 3 parameters or 3 things we might want to do. So how can we visualize or understand a space that's more than 3 dimensions? Well, we talked about how every option can be defined as its coordinates. And now let's think of each of those coordinates as a line where wherever it intersects this axis is its position, right? So that would be its window width, and then its fin depth, that represents the red option. Well, now we can adjust these coordinates into parallel coordinates. And now we can add as many as we want. So as I add these different metrics, let's say, that line and where it intersects over top of the axis represents a new unique option. So we can keep adding as many of these as we want in a very, very complex space where all of these lines represent all of those design options. But critically, I can see them all at once. I can see them unrolled. I can now begin to interpret and understand the entire space at once. Now this is almost comically confusing. But the point is, this is a parallel coordinate graph that allows you to look at a vast amount of data in a complex system within one flat 2D frame. So what we've shown here is that when I say model, we're not talking about a single static design anymore. We're now talking about modeling the challenge, modeling the whole, and then simulating it, generating the full design space so that we can then explore the whole space of possibilities. And that's what we call design space thinking, breaking out of the mold of developing only a few options and instead attempting to understand the larger system, the design system at play. Because if we know more, knowledge is power, we can then design better. So this is a big shift in our mindset. And why do all of that? Well, in the end of the day, it's to mine it for information. It's to be able to explore. So let's look at what is now possible now that we're able to build a parametric model and to generate all the data that represents the whole space. What can we now do with it? So the easiest way that I would recommend is to use a free website called Design Explorer. Actually, the whole reason I put together that parallel coordinate plot example was so that we could go through this, because this is a very confusing website if it's the first time you've ever used a parallel coordinate plot. So a big shout out to Thornton Tomasetti for developing this and allowing everyone to use it. This is a very easy, it's very easy to produce data for this to read. I recommend looking into the Calibri component for Grasshopper. It allows you to iterate any parametric model and to generate the data and the images in this format so that you can just load it up. So we're not going to go through that today. I'll just show you the results. So if this here is a, say, daylighting example for a similar facade that we looked at, just a variety of depths of our space, window to wall ratio, ceiling height, glazing VLT, and orientation. Well, if I were to choose, say, one of these, this line pops up. So this design is 30 feet deep. It's got a large window to wall ratio, see a lot of glass there. It's a short ceiling height, and it's got about a 55% VLT, and it's north facing. And over here, I have my metrics. So SDA 300, this is a daylighting metric, says how much light. Higher is better. And here is a glare metric. Lower is better. So one way that we can use all of this data, one way we can explore the design space, say, let's find the best options. So I can isolate out only the best daylighting performers with the lowest glare. So these are my ideal designs. Now you'll notice they are all nearly the same. They're all very shallow with lots of glass, very high ceilings, and they're all north facing. Now I can't make a building that's all north facing with all glass, right? Because very often our goal here with design space exploration is not to optimize, not to find the best option, because there's no such thing as a best option. It's the best you can do or the best you can justify. There are so many other factors at play that we need to balance. The goal here is to understand which design decisions make the most sense so that we as designers are able to make informed decisions. So here, maybe there's another way that we can look at this data to inform our process. Rather than isolating out the best options, let's flip it and look at which design decisions have the biggest impact. So if I look at glazing VLT, here I have color coded. You see it's kind of muddy. There's no real rhyme or reason. But if I color code by depth, suddenly a pattern emerges. We see that all the high-performing daylighting spaces all are very shallow depth, because this design decision, how deep am I going to make my floor plate, has a much bigger impact than what my glazing VLT is. And same thing with window to wall ratio, you'll see some patterns here. So you can begin to go through and look at which design decisions make the most sense, or let's assume that it's not feasible to have a ceiling height any higher than 10 feet, okay? And due to energy codes, I have to have the window to wall ratio less than this. Here I am, I'm slicing and filtering my design space to see what is possible. So now when I say I want great daylighting, let's see, I only have very few options left. maybe I need to release my constraints a little bit or target a lower performance. Or at least now I know that if I've made these decisions, this is the best that I can do. So here we're able to explore and understand, have a conversation about our design process. We're not saying, traditionally we'd say, how about this design? And the consultant say, all right, I'll get back to you in a week with an answer. Well, that's not good enough anymore. And here you can see that we can now converse and discuss and look at the information and chart a path forward in real time in a single meeting, if you will, once all this data is generated. So it's a very powerful process. Let's bring up the presentation again. And now that we have all of this data, we're in a brave new world where we're able to leverage statistics and machine learning and all these fancy algorithms to do even more with data. So Design Explorer is a very easy way to visually just look through all the data. But we can bring to bear some more advanced means as well. And one I'm going to talk about here is using machine learning as a regressor algorithm in order to provide real-time tools. So the parametric model takes some inputs, runs it through the model, and then develops an output. This could take, for a daylighting calc that we just saw, that might take 5 minutes or even 5 hours to run a single simulation. It can be very slow. But if you set it running overnight, you generate a lot of inputs and outputs. What machine learning can do is essentially learn the patterns between the inputs and the outputs. And for a regressor is like a best fit line. So you can imagine a cloud of points, and you can learn a line through them where you can then predict new values. So if this machine learning algorithm takes all this data of our design space, it sucks it in, then if I feed it new inputs, it'll be able to predict a new output. And critically, this essentially replaces the parametric model. This slow simulation engine can now be inferred and predicted by this algorithm. Whereas, as I said, 5 minutes or 5 hours for one simulation, I can now run 50,000 in a second because it's very simple math now, which enables real-time tools. Also, it helps us understand. So in the graph on the left was all simulated data. I only had 4 window-to-wall ratios that I simulated, so I only have data for those 4 points. What if I have a new design that's in between? Well, the predicted data can interpolate between, and I can then see the whole space. Also, it allows us to create these new dashboards where, if we show in this video here, if our current designs might be right here, and if I were to change a parameter, you can see that would be moving over to a new option. Using a traditional process or even a normal parametric process, I would only discover the results as soon as I arrived at it. But if I have them all pre-simulated, I can understand where a similar or a certain performance might be. So it almost acts like a flashlight leading the way ahead of me. So I can then play and discover and have a map to tell me where I may need to go. It also opens up a lot of new possibilities. You can use basic multiple linear regression to get some quick understanding of the impacts of certain design decisions to understand design drivers. You can use clustering algorithms to understand different regions of the space. And you can use a variety of other methods to understand very complex multidimensional data. So there's a lot that we can do here. All right, so if that's a design space, I then want to talk about this idea of universal design spaces, which I believe is an exciting application of design space thinking that will be very useful for our industry. So let's look at universal design spaces. The idea is that we want to have all this information ahead of time so that we can inform design decisions as they're happening. And this idea of having it before it's needed requires you to pre-simulate. And some of these simulations can take quite a long time. For example, I said 5 minutes per run, and you need to run 1,000. That's quite a long time. So what we need to do is try to, the idea is that common problems can be reused over and over again, which makes it far more worthwhile and feasible to spend the time needed to develop a design space if it can be reused for maybe all future projects. You can then maybe design or run even larger spaces. So let's look at what it would take to create a universal design space for daylighting. So that previous model we looked at, which was a specific facade design, well, what if we created a more generic facade that we can then use to understand how any future, more specific design could be. Because if you break down a problem into its constituent parts, very often we have the same problems over and over and over again. And many facades have very similar features. And so let's look at what it would take to break down a facade into common features that can represent any design you might come up with. So let's begin location. Let's say we choose 2 locations, and if each calc takes 5 minutes, this will be 10 minutes total. Now we might have orientation. So we have now 2 locations, 4 orientations. That's 8 total. That's going to take 40 minutes to run. If we add depth, 3 ceiling heights, you see we're now up to 6 hours. So what we're doing here is I'm going through and showing you how these different features quickly explode exponentially and take quite a long time to simulate. Window width, space between the windows, the sill height. Here we are with over 2,000 iterations. It's going to take you about 8 days to calculate. Different wall thicknesses for glazing types. We're up to 3 months now, 27 iterations. Interior window shading, the blinds that you pull. How about exterior shades? How about the different sizes of these exterior shades? Context, all of these things matter. See, now we're up to 4 million iterations. It would take about 40 years for us to run, even at only 5 minutes each. So this is to say that you can't simulate everything. There is no silver bullet that we can use. However, maybe there's a way to make this more feasible, because 5 minutes of calculation, this is using traditional computational methods. But knowing that it would be very valuable to maybe have all of this data ahead of time, we think that there's a way, and this is what Dr. SmithGroup was working on, there's a way to improve our calculation process to be more appropriate for iterative simulations, whereas right now they're all optimized to run a single design once. Well, what if we wanted to run 4 million design options? Is there a way to make this faster? So if we look at a traditional calculation, it takes every point in your space and it's going to bounce the light through the space, through all your modeling and your geometry, all the way out to the sky. Now you can imagine that if I were to change, say, the ceiling height or one of these interior parameters, the amount of light that comes from the sky that bounces through the context and strikes the window isn't going to change because nothing out there changed at all. I only changed things on the inside. Yet I'm recalculating all of the rays bouncing on the outside, even though nothing has changed. It's very, very wasteful if I'm doing iterative calcs. I'm recalculating the same thing over and over again. So instead we can use, in this case, a 3-phase daylighting simulation, which means that we split the calculation into 3 parts. We measure how the light bounces from every point to the window. We measure how light goes through the window and the transmittance of the glazing. And then we measure how light goes from the window to the sky, how the context affects it. And by splitting it into these 3 different features, we're able to dramatically improve the performance. So what used to take 40 years, if you now look at all the parameters on the inside, rather than 3 million total iterations, instead for the interior, all of those parameters create about 860. It only takes a couple days to calculate that. Only 12 for the glazing calculation, another 100 for the outside, because rather than having them all multiply together, which is where that curse of dimensionality comes in, because it exponentially grows, by splitting them into different groups and adding them, we went from 3 million to about 1,000 different runs, going from 40 years to about 4 months. Now, 4 months might sound like a very, because we need to recombine all of these, and that's where it takes a long time still. But 4 months is actually feasible because this was timed for 1 computer. Well, I can send this to the cloud and do that calculation affordably now. And if this means that if I had all this data and it could give me actionable and great daylighting analysis for any design immediately, that would provide us nearly, once it's done, it'll be free daylighting analysis for every project instantaneously through the future, which is worth paying for a little bit of cloud computing. So what we mean to say is that with improved computation methods designed for this way of thinking and working, this is possible, and this can empower a new type of analysis. So this idea of having a universal design space, a data set that can represent any design we might think of, puts in our hands knowledge and information that allows us to understand the impacts of our design decisions before we make them. So that problem of needing a design to analyze before you can understand your impacts is no longer true. Those constraints of the past do not exist anymore. As we've shown in this meeting, design space exploration, which allows a new approach to informing design, which we think can dramatically improve our industry. So some of the pros of design space exploration, it sort of naturally can identify optimal solutions because you can just simply search the database and spit out the best as you define it. It also provides multivariable sensitivity analysis. So it's not extra work to do this. This is just part of the process. And that multivariate analysis will support a dialogue within integrated teams, which is very, very important because you can then have a discussion about which criteria should be prioritized over others. And it's all in that discussion is informed with data. Predictive analytics can inform the design decisions, so you're not reacting to different solutions. You're not saying, how about which of the 4 is best? I'll choose option 2. No, now we're understanding. The universal design space idea that we just discussed is critical because it can be reused. This can also be shared. So Dr. Mishra and I are discussing creating these data sets and then providing them for the industry. Other industries have this. They have common reusable data for the profession. I think architecture needs to follow suit so that we're all not competing over who has the best Excel spreadsheet, right? We can develop the best data and then all use that to build our own unique tools from it. And then also, once we have all this data, machine learning models can enable real-time simulation tools. So this can give us a whole new generation of digital assistants. We've barely scratched the surface on what is possible, but it's very exciting. Now on the cons, because this all isn't perfect, the model setup and simulation still takes a long time. Developing and designing this parametric model to work right, especially if you're trying to build a universal model, is going to take some skills. It's going to take some time. And very often it's difficult to do that under the time constraints of a single project. In this way of working, we're all not trained this way. So creating the right design space requires a new thought process, a new skill set. Students coming out of school will likely have these skills, but for professionals in the industry right now, we need to take some night classes. We need to watch some tutorials because this is a new way of thinking. Speaking of new way of thinking, too much data can be confusing. We weren't trained to clean or tidy data or even really to talk about it in school. So that's, I think, a new fundamental skill set that's required in order to work this way, is for our design teams to get a better understanding of complex data. Also, to be most effective, design space exploration requires a cultural shift. We need to move away from the black cape architect into a more open design process so that we can leverage this information. Because if we have all the information in the world, it doesn't matter if we're not listening to it. So we need design teams that are open to a collaborative design process. And then another big one here, the current fee structures for our projects pay for project-specific services, right? Analysis for a design. But as we just showed with the universal design space, if we're being paid to do it for not just one project, but for every project, those design tools, perhaps we need more funding up front to do daylight analysis for all projects forever, rather than limiting ourselves to what a single project fee can cover. So our business models aren't set up for this. And all of those are challenges that I think we will, as an industry, be addressing as we move forward. But the point of this presentation was not to give an answer to all of those problems. It was just to maybe open our eyes to what's possible. Because if we take a step back and recognize that the constraints of the past are rapidly falling, and that we have parametric modeling, we have massive amounts of computation, and we have the ability to analyze and leverage data in ways that we never did before. This opens up the possibility of a design process like design space exploration, which once again, you model your challenge rather than your solution. Once that has been modeled parametrically, you can then pre-simulate or generate the design space to create a database that represents your design problem. Once you have that database, you can then explore it and leverage it to develop a new generation of design tools. which will really enable us to inform at the speed of design. And that's design space exploration. So I hope you enjoyed that. And if you have any questions, feel free to email me at leland.curtis@smithgroup.com. Thank you very much.